Welcome students, we've been given this question. A is equal to 1 positive root of 5 divided by 2. We are expected to find the value of a raised to the power 12. I'm sure most of you know how to do this, but I am going to be showing you 3 different ways by which this question can be solved. Foremost, the point of observation here is this is a golden ratio. Now, for the first method, it doesn't matter whether the given quantity is a golden ratio or not. But for the second two methods, because the value of A is a golden ratio, we can apply those methods and reduce the number of steps or the number of algorithms that we have been using to solve this particular question. So, having mentioned that, let us move on. Now, we've been given the value of A to be as 1 positive root of 5 divided by 2. So, what I would do is I would multiply A with 2. It's cross multiplying. So, it's going to be 2 times A is equal to 1 positive root of 5. Now, if I were to move this to the other side, I would get 2A negative 1 is equal to root of 5. I would be squaring both sides. So when I square both sides, I would get 2a negative 1 raised to the power 2 is equal to root of 5 raised to the power 2. I would like to use this side. So this is going to be 4 times a squared negative 4 times a positive 1 is equal to 5. I would move 4a with the negative sign to the right hand side, so that would give me 5 positive 4 times a. I will also move this positive 1 to the other side. That's going to be negative 1. So 5 added with negative 1 would give me 4. There's already a 4a there. So now I would take this 4 out and rewrite this as 1 positive a. Of course, on the left hand side I got a 4a squared. Clearly the 4 and the 4 can be cancelled. So now I have a relation connecting a squared with 1 positive a. So this is the most important equation that we will be using to solve our question. Now let us consider the given quantity a raised to the power 12. Now I can rewrite this as a squared raised to the power of 6. Fair enough, right? Now in place of a squared, I would like to substitute the value of a squared, which is 1 positive a. Now this is raised to the power of 6. I'm going to use the law of indices. A raised to the power of m raised to the power of n can be written as a raised to the power of n times m, or it can also be rewritten as a raised to the power of n times m. So all of these deductions are possible. So I'm going to rewrite this as 1 positive a raised to the power of 3, and this is in turn is raised to the power of 2. I can rewrite it like this. Now what I wish to do is, instead of having the 3 inside and 2 outside, I would like to rewrite this as 1 positive a raised to the power of 2 raised to the power of 3. So this is exactly what the law of indices permits us to do. Now I can expand this. If I were to expand this 1 positive a raised to the power 2, I would get 1 positive 2 times a positive a squared raised to the power of 3. That's fine. Now again I would be using a squared is equal to 1 positive a over here. So that would give me 1 positive 2 times a positive 1 positive a raised to the power of 3. I can add 1 with 1. I can add 2a with a. So that would give me 2 positive 3a raised to the power of 3. Now what I wish to do is I would like to use a positive b raised to the power of 3, which is a cubed positive b cubed positive 3a squared b positive 3ab squared. This is the formula. If I were to use this formula, this is going to be 2 cubed positive 3a raised to the power of 3 positive 3 times a squared times b positive 3 times a times b squared. So if I were to expand this, this is 2 cubed 8, 3 raised to the power of 3 will give me 27, a cubed positive 2 raised to the power of 2 will give me 4, 4 times 3 12, 12 times 3 will give me 36a positive 3 squared is 9, 9 times 2 is 18, 18 times 3, 8 3s are 24, 2, that's going to be 54. So I get a 54a squared. So this is what the expansion that I have acquired for. Now the question is, I will have to expand and neutralize this. So 27a cubed, I would be rewriting that as a times a squared, positive 36a, positive 54. A squared, I can replace a squared as 1 positive a, so that's going to be 1 positive a there. Now this is going to be 8 positive 27a, a squared is 1 positive a, positive 36a, positive 54, positive 54a. This is 8 positive 27a times 1 is 27a. This is 27a squared, positive 36a, positive 54, positive 54a. Now what I can do is I can replace a squared as 1 positive a again. So this is going to be 8 positive 27a, positive 27 times 1 positive a, positive 36a, positive 54, positive 54a. I can rewrite this again, 8 positive 27a, positive 27, positive 27a, positive 36a, positive 54, positive 54a. You can clearly see the right hand side consists just of constant term and a term. So first I would add 8 with 27, that will give me 35. 35 added with 54 will give me 89. So I have a 89 as a constant, write that down. Now let me add the a term. So 27a added with 27a, that's going to be 54. 7, 14, 1, 54a. So this is done. I got a 36a added, 36a, 6 added with 4, 10, 1, 90a, and I've got a 54a. So this is going to be 4, 14a. Okay, that's fine. So this is going to be 144a. On the left hand side, I've got a raised to the power of 12. Now since a is 1 positive root of 5 divided by 2, I can substitute it here. So this is going to be 89 positive 144 times of 1 positive root of 5 of 2. Now I can rewrite this as 89 positive 2 divides 14, 7 times 7, that's going to be 2 there. So this is 72 positive 72 times root of 5. Now I can add these two together, 89 and 72, that's 11, 1, 161. So 161 positive 72 root of 5. This is my a raised to the power 12. Now of course if you want to calculate, you can always use the value for root of 5. You can find that out and then you can compute it to be a value, but that is not necessary. So this is okay. Now the most important point is, to achieve this we have to perform so many steps, right? See the list of instructions that we will have to provide just to arrive at a raised to the power 12. Now I'm going to show you a very powerful method by which we can just reduce all of these by a fraction. Now this is method number 2, right? Method number 2. Now we know that a squared is equal to 1 positive a. Now what I wish to do is I would like to multiply by a both sides. So this would give me a raised to the power 3 followed by a positive a squared. But a squared is 1 positive a, so let me substitute that. So it's going to be a positive of 1 positive a. I can rewrite this as 1 positive 2 times a. Now I'm going to multiply this again by a. So this is going to be a power 4 is equal to a positive 2 times a squared. I'm going to rewrite this as a positive 2 of a squared is 1 positive a. So substitute that. This is going to be a positive 2 times a. I can actually rewrite this as 2 positive, add a with 2a. That is going to give you 3a. Now multiply this by a again. This is going to be a power 5 is equal to 2 times a positive 3 times a squared. Now my a squared is 1 positive a. This is going to be 2 times a, positive 3 times a. I can rewrite this as 3 positive. You add up these two things, you get 5a. Now one more time, I want to multiply this by a. I get a power 6 is equal to 3a positive 5 times a squared. I can rewrite this as a positive 5 of 1 positive a, which is 3a positive 5a. Now this can be rewritten as 5 positive 8a. Now what I wish to do is I wish to create a table. Okay, so let me show. Now this table is going to comprise of 3 headings. So one is going to be exponent, okay, and then the next is a coefficient, and the final term is going to be the constant term. Now I'm going to start off with degree 2, okay, degree 3, degree 4, degree 5, degree 6, and so on. Now find out the coefficient of a in degree 2. It is 1. In degree 3 it is 2. In degree 4 it is 3. In degree 5 it is 5. In degree 6 it is 8. Okay, now find out the constant term. In degree 2 constant is 1. In degree 3 constant is 1. In degree 4 constant is 2. In degree 5 constant is 3. In degree 6 constant is 5. So you got this table. Now how are we going to use this table? Let me show you this to you. Now just observe the coefficient of a. What do you see? Observe the constant term. What do you see? Have you got that? Now if you were to observe the coefficient of a, clearly this is a Fibonacci series. So if you would refresh your mind with regard to the Fibonacci starts with 1, 1. You add the quantity to the previous, you get 2. You add it to the previous, you get 3. You add it to the previous, you get it 5. You add it to the previous, you get 8. You add it to the previous, you get 13. You add it to the previous, you get 21. You add it to the previous, you get 34. Add it to the previous, you get 55. You add it to the previous, you get 89. You add it to the previous, you get 144. Okay, let's have that. So this is the A's coefficient. Okay, the coefficient of A. Now this is exactly what is present, but the only thing is that this starts from 1. It starts from 1. You see that? 1, 2, 3, 5, 8. 1, 2, 3, 5, 8. But we don't have this 1 here. And with regard to the constant term, this is again a Fibonacci. It starts from 1. 1, 1, 2, 3, 5. So if I were to write it, ignoring this 1, and starting off the constant term, I just want to write the constant term. So the constant term is going to be 1, 1, is going to be 2, add the previous term, you get 3, add the previous term, you get 5, add to the previous term, you get 8, add to the previous term, you get 13, add to the previous term 21, add to the previous term, you get 34, add to the previous term, you get 55, add to the previous term, you get 89. That's enough. Now why am I saying it's enough? Because if you were to look into the exponents, okay, we started with degree 2, a squared, okay, this is 3, this is 4, this is 5, degree 6, degree 7, degree 8, degree 9, degree 10, degree 11, degree 12. So this is a raised to the power 12. Now if you want to write a raised to the power 12, now let me draw your attention over here. If I want to write a cubed, then it is going to be a constant plus some constant times a. This is going to be the pattern you will find all across. A power 4 constant plus a constant times a. A power 5 a constant plus a constant times a. A power 6 a constant plus a constant times a. So a power 12 is going to be what? Is going to be constant plus constant times a. So what is the constant for a power 12? 89 plus 144 times A. This is A raised to the power 12. So let me move up. Now what is A? A is equal to 1 positive root of 5 divided by 2, right? So therefore A raised to the power 12 is equal to 89 positive. In place of A, I will substitute this quantity. So it's going to be 144 times 1 positive root of 5 divided by 2. 2 divides here 7 2 times. So 89 positive 72 times 1 positive 72 times root of 5. You add these two things together, 89 added with 72, 11, 161, right? So place the values. So it's going to be 161 positive 72 times root of 5, which is nothing but A raised to the power 12. Now this is the solution, and this is what we have got in the previous case. By doing all of this, you see the process that we did. Okay, so we have just ignored, or I would say we have got rid of all of these process, and using the expansion for A squared is equal to 1 positive A, we were able to relate to the Fibonacci sequence, and from the Fibonacci sequence we were able to obtain a relationship between A raised to the power 12 and constant term plus the constant times A. So this is one way. Okay, now I would like to show you another way, and this way is largely due to the fact that A is given to be as 1 positive root of 5 divided by 2, which is a golden ratio, and we are able to do this just because of this particular fact that we have a golden ratio. So let me just show you that method. So this is going to be method number 3. The statement is as follows. Now, given A to be the golden ratio, then A raised to the power of x can be written as f of x. Of course, this has to be product multiplied with A, positive f of x negative 1, where f of x and f of x negative 1 are Fibonacci sequence numbers. Okay, this means for x is equal to 12, we got A raised to the power 12 is equal to f of 12 times A positive f of 12 negative 1. Now what is f of 12? Just go and check it out. F of 12 is 144, f of 11 is 89. So this is going to be f of 12 is 144 times A positive f of 11 is 89, which is equal to A raised to the power 12. Now clearly you can substitute the value of A here, and we would arrive at the same point, and subsequently we will be able to find out that A raised to the power 12 to be as 161 positive 72 times root 5. So you see that the number of lines, all that we need to do here is to know this relationship. Once we know this relationship, we will be able to obtain A raised to the power 12. So as I mentioned to you, for the first method, instead of A to be as 1 positive root 5 over 12, if they were to give you any quantity for that matter, you can follow this algebraic procedure. So it is important that you know how to use algebra to extract the value of A raised to the power 12. And along with that, it is also important to know and connect mathematical concepts to the given question. Why? Because it drastically reduces time, and in this age, anything that reduces time means efficiency, and efficiency means productivity, and productivity means prosperity. Thank you, students. Enjoy your night.